Okay, so in 5.2, number 35,
Yes.
I have 17% of a radioactive substance decays in 5 hours.
Yes.
Okay, so I got the 5 hours part of that. But what's the thing that happens in 5 hours?
17% of the substance decay.
Which means what?
0.17
0.17
is left.
uh,
To zero.
is gone, right?
Yeah.
So if 0.17 is gone, what does that mean? How much is there? 0.83. Nice. That means 0.83 is left. Does that make sense?
Yeah.
Okay. And then what's the half-life is the question, right? Okay, so how do you do half-life things?
You do 0.83 Q of O e to the k to the 5 equals
Hang on. 0.83 equals,
no, to 0.83 times Q of O e k to the 5 equals, and then you do 0.3 plus 0.83, which is something Q to the O, because then you'll get 1 and 2 on.
oh, I see
You
what
know
you're
what I'm
kind of
trying to
shooting
do?
for.
Yeah.
Yeah. Okay, so first things first, I think what I have is that 0.83 is left, right, after
Yeah.
5 hours. So I think that kind of the equation I'm operating with is something like Q of t is Q of 0 times e to the k times 5. Oops, k times
Oh, T.
t. And then you're taking this thing and you're evaluating this at 5, right?
Yeah.
So you're saying, okay, so Q at time 5 should be Q at time 0 e to the 5k, right?
Yeah.
And I think you just dorked where you put your 0.83. Is 0.83 the amount you started with, or is it the amount in 5 hours?
It's the amount in 5 hours.
Yeah, so that should go over here.
Oh.
So I think you want 0.83, but it's 83% of what that's left? Yeah, whatever you started with, right? Okay, so what did you start with then? Yeah, you started with 100%, so you should have 0.83 equals 100 e to the 5k. Oh, and I dorked something here. What did I dork?
It's 1 point. It's 0.1, 1.0.
Yeah, so I converted this thing to a decimal, right, from a percent. So this thing should also be converted to a decimal from a percent. You could also do 83 equals 100 e to the 5k. You'll get the same thing. Just make sure you keep your did I convert to a percent or am I in decimal land straight. Right? If you bring 1 to decimal land, you have to bring the other one along with it. Does that make sense? Okay. Once I'm here, what do I do?
Divide by 1.
Okay. Divide by 1.
Yes.
Divide by 100%.
Okay.
How's this?
It's a really chill step. Yeah, basically drop the 1, right? You don't need that. Then what?
Take your natural log of both sides.
Then natural log both sides.
And then divide by
Yes.
Damn it.
There's the
It looks close. All right, so I got natural log of 0.83 is what? 5 times k, and then I multiply by 1 over 5, right? So I got log of 0.83 over 5 is k.
Yeah.
Yeah. Then what?
Simplify that shit.
You evaluate to find your K.
Okay, so you could get an approximation.
Negative 0.03727.
Negative 0.0 what?
3727.
Okay. round someplace.
Oh, wait, yeah, you're right. No, you're not. Yes, you are.
2 sig figs.
I may well have heard you wrong. Is this a
Yeah.
correct rounding of what you have?
Nailed it.
Okay. So, round someplace, doesn't matter which. In chemistry class, you might want to think about sig figs or something. Right?
Oh yeah.
But whatever. Okay. Then you what with this?
Plug it back into K.
Plug it back into K. So that should go back in this one over here. Right? So now I know that Q of T is Q0 e to the what? That minus 0.0373 times T. And really this is kind of approximately,
Yeah.
right? But it's a model anyway, so it's kind of an approximation anyway. Okay? What else? That's not the answer.
You put a 1 there.
Put a 1 here and a
Solve for 0.5.
1/2 over here.
Oh, yeah, 'cause that's hard.
Or a 2 here, right, and a 1 there. Whatever. So now I'm solving for the half-life, right? So I do 1/2 is e to the minus 0.0373 t. And then I'll log and divide and get t is whatever it is. So those two steps should be log and then divide by negative 0.0373. And then just make sure you don't forget the parentheses in your calculator. Anybody do this a different way? There is another way available. No? That's not what I got. What did they get?
18.6.
What did you get?
Negative 13.4.
You did not get negative anything. Put it in your calculator wrong?
I don't know.
So why shouldn't you have gotten negative anything?
Because you're dividing.
Oh, yeah.
Because you can't go back. You can't. Yeah.
When you log a half, right, you're going to get a negative number, and then you're dividing by a negative number. Better get a positive number out of that. Or alternatively, it only went down 70% in 5 hours, right? The half-life better be bigger than 5. Just with me on that?
Calculator error.
Find it.
Yeah.
You were missing a parenthesis.
No, I was missing an L in.
That'll do it too. Okay, another way you could do this is instead of using this guy, Q of T is Q0 e to the kt, you could use the one that's better for half-lives, which is Q of T is Q0 1/2 to the kt.
Sure.
And then the K will be 1 over the half-life. Cool?
See, question.
Yeah.
So when I read this, it said it's read like if 17% of a radioactive substance decays in 5 hours. All right, so I read it and I was thinking that it meant like you had 17% of this substance left and it decayed to 0 from there.
Oh.
Could you solve that? Just curious.
No, it'll never
I was-
decay to 0 in finite time.
Okay.
This is
Oh,
one of the
you'll
difference
only
between the
approach it-
model and the reality,
you'll
right?
only approach it.
Like, the reality is, well, okay, don't quote me on this in terms of chemistry, but I believe the reality is that radioactive material is made out of atoms, just like everything else, right?
Yeah.
Yeah?
Sure.
Okay, and so all those little atoms are like this, yeah?
Yeah.
Okay.
And if you have a blob of radioactive substance, there is some finite number of atoms in there,
True.
right? So if you kind of let this sit for long enough, eventually there will be one atom left. And then that atom will either decay or not. right? And you could like sit there and watch it.
For a very long time.
And eventually it would probably go away, right? The probability of it going away approaches 1 as you continue time towards infinity, right? So it is physically possible for radioactive substance to decay to nothing, but mathematically the model we get is this E model, right?
Right.
And that exponential function is never actually going to get to 0, it's just going to approach 0. And the difference there is kind of this thing's modeling the probabilities, and sitting there and watching that one atom is kind of getting a realization of a probability. So that's why I'm not super worried about the approximate E equals here versus the hard equals here. You're already approximating this anyway. You guys cool with that?
We do 43.